Section 7.2 is about upper triangular matrices, and kind of a subtitle is that upper triangular matrices are important because they are the second best thing to diagonal matrices. And it turns out that many times we don't have diagonal matrices, but we can always have upper triangular matrices. Before we start about upper triangular matrices, I would really like to talk about the diagonal matrices, which is the ultimate goal. And first of all, we have an observation that if we have B bases with basis vectors v1, v2, vn, basis in vector space V, and we have an operator, linear operator T, then what we have is that T has a diagonal matrix with respect to basis B if and only if TVI equals to lambda I VI. That is, each vector in the basis is an eigenvector of T, and lambda i's are eigenvalues. So this is quite simple to look at. Let's say that we have an A matrix, which is the matrix of the transformation in basis B, and it has lambda 1, lambda 2, lambda n in the diagonal and 0 everywhere else. Then by definition of the matrix of the transformation, lambda 1 is the image of the first vector, basis vector, in the B basis, and the last one, lambda n, or I mean the column vector actually, is the image of the Vn basis vector in the B basis. In general, the image of the ith vector in the B basis equals to 0 everywhere else except the ith component is lambda I, which means the ith component is the coefficient of the Vi basis vector, which exactly means that Tvi equals to lambda I Vi. And since none of these Vi's are 0 vectors, that means the only way it's possible is that lambda I is an eigenvalue and Vi is an eigenvector. And then in general, this is very nice to have a diagonal matrix because it's easy to work with, especially, for example, if all the diagonal entries are the same, then it's just a multiplication with lambda. But even if they are different, if you have a vector with components x1, xn, then A times this vector is just lambda times x1, lambda 2 times x2, and lambda n times xn. So it's just multiplication of the components with one scalar. So if you compare this to regular matrix vector multiplication, it's much simpler. Instead of n sum linear combinations for each row of the matrix, we just have one scalar product of the component. So this is very simple. And in the previous section, we saw how to find the eigenvalues and the corresponding eigenspace when we have one-dimensional eigenspace with one-dimensional space that is invariant under the transformation. Many times, unfortunately, we don't have this, that we find one-dimensional eigenspaces. Already in the homework assignment, we saw some of this, but let me review. For example, so in the previous section we had section 1, we had one-dimensional subspaces that were T-invariant. So what we had was that we had null spaces of T minus lambda I. So we had homework assignments to calculate this null space, or a basis for the null space, and also to calculate the eigenvalues from the characteristic equation that was obtained using the characteristic polynomial, which is usually written as xi minus the matrix of the transformation in some basis. In some cases, in the homework assignment, we obtained complex or real numbers for the eigenvalues. And as calculation goes, that's not a problem. The problem is when we start talking about vector spaces. So if, for example, V is a vector space, for example, R2, and for example, if F, the scalar field, is all R, real numbers, and for example, we have A from R2 to R2, so it's a linear operator on R2, defined by the matrix 0, 1, minus 1, 0. So when you want to calculate the characteristic polynomial, we get the determinant of xi minus a, which is the determinant of x minus 1, 1, x. We get x squared plus 1. Then we set this equal to 0, and we obtain from this equation the eigenvalues, lambda equals plus or minus I, the imaginary unit, since we have to take the square root of minus 1 if we rearrange this equation. Then the problem is that this is not a real number. And for example, if you want to calculate the null space of t minus lambda I, for example, take lambda equals to plus I, what we get is minus I, 1, minus 1, minus I. And then you want to solve this when you set this equal to 0, so the augmented matrix is minus I, 1, 0, minus 1, minus I. Then we have to start working with complex numbers, so we multiply, for example, the first equation with I to get 1 there, 1, I, 0, and then we add this to the second equation. Then we get that x1 plus I x2 equals 0, and then from here we get the eigenvector, one eigenvector, as minus I x2 x2, or x2 minus I1, which is unfortunately not in R2. So that means that we don't get, this sounds like a nice calculation, but actually we don't get a subspace in R2 as a null space. What we get instead is a subspace in the C2 complex space. So this is a problem to work with sometimes to work with real numbers. The reason why this whole thing happened is that we had this equation x squared plus 1. This was a polynomial, and we assumed real argument x and also real coefficients. Yeah, 1 for x squared, 0 for x, and 1 for the constant term. So very nice real coefficients. But then it doesn't have root in the real numbers. So we worked with real numbers, and suddenly we obtained that there are no roots. So what we say about this kind of polynomial is that this is not algebraically closed, the real numbers, the set of real numbers. And in general, we say that a field f is algebraically closed. For example, if there is a definition and then there are equivalent statements that can be used in calculations. So one definition would be is algebraically closed if polynomials with variable in f and coefficients in f have roots in f. So in this section, mostly we will work with algebraically closed fields. Let me also mention about this example where we had a matrix 0, 1, minus 1, 0. If you look at its effect on a vector xy, 0, 1, minus 1, 0, multiplying the xy vector we get that this is y and minus x. And if you want to look at this in general, in the xy plane, what the effect of the matrix is, let's say that we have here an x value and a y value, then what it does is, with this vector, the xy vector, it turns the first coordinate into y. So if this y was small, then now the first component will be small, and then x becomes minus x. The second component will be minus x. So here is minus x. That means the new vector, if that was the x vector, then this is the ax vector. So that means that if this angle was here, this small angle, then this is the same. And that means that the angle between the old vector and the new vector is 90 degrees. So this is actually a rotation, clockwise rotation with 90 degrees. And then if you think about what it does, it rotates the whole two-dimensional space. So it is kind of easy to see visually or understand visually why there is no one-dimensional A-invariant subspace. That would be line, one-dimensional subspace would be a line going through the origin, but none of them stay A-invariant, none of them stay unaffected by the rotation. When you rotate a line, it gets rotated. No line stays invariant. So this is an example where there is no A-invariant subspace for a transformation in R2. Note that without a proof, we will have that C is algebraically closed. Mostly we will work with actually real coefficients and real variables, but even if we started with complex coefficients and complex variables, a polynomial would always have solution in C, in the complex set. Note also, so let's discuss upper triangular matrices. A, the determinant of the matrix equals to the product of the diagonal entries. This was mentioned when we discussed the determinant of matrices. This is one important thing that we will use. The other one is that A is invertible if and only if, I'm not sure if I used this notation before, IFF stands for if and only if, the determinant of A is not 0, which now means that none of the diagonal entries are zeros. And also, for linear operators, if you have lambda eigenvalue, and then we have v eigenvector, we have that t minus lambda I applied to v is the zero vector, which means the non-zero vector v is mapped to the zero vector. Of course, also the zero vector is mapped to the zero vector under all linear transformations. Now this is not t, this is t minus lambda I. So two different vectors are mapped assigned to the zero vector. That means t minus lambda I is not invertible since it's not one-to-one. So these are some basic remarks about, in general, operators and about upper triangular matrices. Let's see the first important theorem in this section. Let V be a non-zero finite dimensional vector space over an algebraically closed field F. Then each linear operator on V has an eigenvalue. So note that this doesn't say how many, it doesn't say whether they're different or repeated, it just says has an eigenvalue. The proof is a nice application of linearly independent vectors. We denote with n the dimension, non-zero, positive number, since it's a non-zero vector space. We choose a non-zero vector v in this set V. So we consider the list consisting of vectors v, tv, t square v, up to tn applied to v, where we have this n being the dimension of the vector space. What we have here, if you count how many vectors we have in this list, this is of n plus 1 vectors. And this is in an n-dimensional space, because V was n-dimensional. So that means this cannot be linearly independent. The list must be linearly dependent. We have too many vectors for the list to be linearly independent. That means there are scalars, scalar coefficients, such that there is a non-trivial linear combination denoted by a0v plus a1 tv plus an tnv, such that this non-trivial linear combination gives you the zero vector. These coefficients a0, an are from this field, scalar field. Then let m be the largest index, such that the corresponding coefficient is not zero. Now some of these vectors might be zeros. We don't exactly know what happens when you apply t or t squared or t cubed to v. But we know for sure that v is not the zero vector. That was our choice, to choose non-zero vector v. So that means a1, an are not all zeros, because if that was the case, then we would have simply a0 v, and that would force a0 equals 0, which means all zeros coefficients. But that would be a contradiction to be a non-trivial linear combination. So some of the a1s are not zeros for sure. That means there is a largest index, which is not zero. So we consider then only that part of the polynomial, and we create a polynomial a0, a1z, am, zm. And then, because this is a algebraically closed scalar field, f, only for this reason we know that we can factor this polynomial using some roots, using the roots of the polynomial. Z minus lambda 1 times z minus lambda 2 times z minus lambda m. By the way, am is supposed to be the multiplier of zm, so this coefficient should be am. It's a minor detail. So what we have is that am is not zero, and this equation holds. So am is from the field f. Also these lambdas are from f, going from 1 to m, and this equation holds also for all z from the algebraically closed scalar field f. So this means that this initial linear combination that we wrote as a0 v plus a1 tv plus ant to the nv, stopping at the coefficient that's not zero, that means it's enough to write the first m of these, because the rest of the coefficients are zeros. Also note that since these are all linear operations, we can actually factor out v at the end and write a0i plus a1t plus am t to the m. This together multiplying the v vector. We apply this transformation to the v vector. And factoring this polynomial then is the same as factoring the polynomial equation in the operator t. Instead of the factor z minus lambda 1, we get t minus lambda I, and so on. We get t minus lambda 2i, with all the factors having z replaced with t, and lambda replaced with lambda times the identity matrix. So the way we apply this operator is that we start applying from the right hand side. So we have that this is the zero vector. Let me write down again the zero at the end. Then we have the following option. So these are cases. First case, if already this first one is zero, t minus lambda mi v is zero, then that means that lambda m is an eigenvalue and v is an eigenvector corresponding to this lambda. This is not the case, then we have still the possibility that this with the previous factor is zero. So t minus lambda m minus 1i and t minus lambda mi applied to V is 0. So in this case, then this is an eigenvalue of t, and this vector will be an eigenvector because it's not 0, since it's not the first case that we have. So if this is not the case, then continuing like this, we have case 3, when we have t minus lambda m minus 2I times t minus lambda m minus 1I times t minus lambda m I v is 0. So this is another possibility. V is outside the product, which means then that lambda m minus 2 is an eigenvalue, and then this would be an eigenvector. So continuing this way, one of the factors will create 0. If nothing else, lambda 1, but one of the factors will have this form that t minus lambda ji multiplies the larger indices. In this case, then lambda j is an eigenvalue, and this is an eigenvector. So this would be the first one factor creates 0, the first such. We have the eigenvalue and also the eigenvector in it. So that finishes the proof. Starting from the right hand side here, we try which factor gives actually the 0. One of them must give the 0. The worst case is that the last one with lambda 1 creates the 0. If all the others are non-zero, then that means that that will be an eigenvector and the lambda 1 will be an eigenvalue. So let me mention again that the goal is to have diagonal matrices, or if nothing else, at least upper triangular matrices. It turns out that upper triangular matrices are always possible. Before we look at this, there is a theorem that will help establish that, and this theorem says that suppose that T is a linear operator on a vector space V, and we have a basis B with basis vectors v1, vn, then the following are equivalent. 1, TB is upper triangular. Second, TVK is in the span of v1, vk for each k going from 1 to n. And the third possibility is, or the third statement is that the span of v1, vk is t invariant, again for each k going from 1 to n. So the proof is not going through all the different equivalences or going in a circle, maybe from 1 to 2, 2 to 3, 3 to 1. Instead of that, we just write down what it means to have a matrix in a basis for a transformation. So we're supposed to have the k column as the kth basis vector image under T, and then this is expanded in the basis B. So if this column vector here has the form A1k through AKK, and then the rest is 0, this is the case if and only if this image of the VK vector in the B basis is equal to the sum as I goes from 1 to k, AIK, VI, which means this is in the span of V1, VK. So this is basically the equivalence of 1 and 2, because this is about 1. If this is true for all k, and this is what the second statement says, that the VK has image in the span of V1, VK list. And then the T invariance means, so if this holds for all k, then since the image of VK is in the span of V1 through VK, that means the image of the span of V1 through VK is also a subset of the span of V1 through VK. Since V1 is actually in the span of V1, V2 is in the span of V1, V2, and VK all we know about Vk is that it's in the span of V1, Vk. And since the linear operator has this linear property, any scalar multiple and any linear combination will be also in the span. And the big theorem of this section is that let F be an algebraically closed field and let V be an n-dimensional vector space over F with the dimension n greater than or equal to 1, and finally let T be a linear operator on V. Then there is a basis B for V such that the matrix of the linear operator in basis B is upper triangular. The proof goes by induction, and the induction is on n, the dimension of V. We start with n equals 1. The V is one-dimensional. In one dimension, no matter what basis actually what you have, this is a 1 by 1 matrix, which is just a number. And by the definition of upper triangular, this is upper triangular. Since the definition of upper triangular is that the lower, under the diagonal, we have zeros. Well, there is the diagonal of the one entry, and there's nothing under it. That's definitely considered to be 0. So for nothing, everything is true. Any entries under the diagonal is 0. There is no entry actually under the diagonal. So this is true. It's trivial that for n equals to 1, this statement is true. So by induction hypothesis, assume that the theorem holds for all vector spaces over F with dimension less than n. So the statement holds for dimension 1 through n minus 1. And now we consider the case n. What we do is we consider an eigenvalue. So T has an eigenvalue, at least one eigenvalue, lambda, according to the previous theorem. Then we consider the subspace U, which is the image of T minus lambda I. So we looked at this a long time ago, that image of a linear mapping is a subspace. And we also know that this is not just the zero set or empty set. So this has a dimension higher than 0. So because of that, what we have is that T minus lambda I is not injective. That means not one-to-one. It follows that it is also not surjective. Actually, I will consider this as a homework to explain why, or to look back previous consideration of dimensional analysis. And then because of that, what we have is that the dimension of U is less than n, which was the dimension of V. Now, for any U vector from this space, vector space U, we can write the image of U under T in a kind of tricky way that we want to introduce this T minus lambda I operator. So we want to separate into one part with T minus lambda I, but then that's not the same. How can we compensate? Well, we compensate simply adding lambda times U to this. So lambda times U actually cancels the minus lambda I U. But the reason we split this TU into this part, because what we have is that this part is in U, and clearly this is in U, because U is a subspace, so any linear combination or multiple of a vector is in U. So that means that this is in the U space. So in fact what we have here is that U is supposed to be, since U equals to the image of T minus lambda I, this is T minus lambda I invariant, but this equation here also shows that U is also T invariant, since any TU vector is also in U, if U was in U. That means that if we restrict T to the U subspace, what we get is a linear operator. And we also have that U has dimension less than n. So according to our induction hypothesis, we can diagonalize TU by choosing an appropriate basis. So there is U1, UM basis in U, such that T restricted to U in this basis, let me denote it with BU, is upper triangular. And then according to the previous remark or previous theorem, what we have is that T of Uj, which is the same as T restricted to U, and then applied to Uj, these basis vectors, is in the span of the previous ones. So what we do here is then we extend the basis of U, this U1, UM, to a basis of V. We did this before, a long time ago again. We extended a linear independent set to a basis of a vector space by adding more and more vectors. So then the basis has the form, we don't really know how many vectors we have to add to this basis of U to get a basis of V. Let's say that we add VR. Clearly what we have is that m plus r equals to n, the dimension of the whole V vector space. Then if you look at the effect of T on one of these V vectors for k between 1 and r, this equals to, like before, we can split this into two parts, one with T minus lambda I Vk, and then the other is lambda times Vk. So U, by definition of U, that was the image of T minus lambda I. So this is actually in the image, that means this is in U. And then this is just in a scalar multiple of Vk. The image was the span of U1, Um. So that means that this is in the span of U1, Um. And then we just add the Vk vector. And in fact, we can increase this a little bit if we don't just add Vk to this span, but we add from V1 to Vk all the vectors. But comparing this, that Tvk is in the span of the vectors from 1 to Vk, according to the previous theorem, we have that in this basis, T is upper triangular matrix. That we denote this matrix with BV. And this completes the proof. As I mentioned at the beginning of the section, we have that T is invertible if and only if none of the diagonal entries in the diagonal matrix TB is 0. There is another corollary to this theorem. Suppose T is a linear operator on V with upper triangular matrix TB with respect to some basis B of V. Then the eigenvalues of T are precisely of the entries on the diagonal of the matrix TB. In fact, we can also rearrange the eigenvalues so that they are ordered and or together if they are repeated. So the proof of this corollary is based on this observation with the invertibility. So let's assume that the diagonal entries of TB equals to the set or vector lambda 1, lambda n. We don't care about whether or not they are repeated or not. And now we consider a general lambda scalar, and we look at the T minus lambda I matrix in this basis B. So this is still upper triangular, and the diagonal entries or elements, which is just lambda 1 minus lambda, lambda 2 minus lambda, lambda n minus lambda. So what we have is that T minus lambda I is not invertible if and only if lambda equals to lambda I for some of the lambdas, at least one I. And also, that means that this lambda is an eigenvalue, which means that the null space of T minus lambda I is not just a zero vector. So note that making TB diagonal, the way we say that is that we diagonalize T, means finding a basis. So that means change of basis. And we did have formulas for change of basis already. So that was when we have P matrix such that PD equals AP for a general matrix A. that means also that D equals to P inverse AP. Here P is supposed to be the new basis, but since the new basis corresponds to the diagonal matrix, that means that D is really the T matrix representation in this P basis. So what we have here is that then we have the eigenvalues in the P basis. That is, this is lambda times, if the P basis is V1, Vn, that means this is lambda times V1 and lambda n times Vn. That basis representation would be the diagonal matrix. So that means that the P matrix is the matrix of eigenvectors. So this is how we diagonalize a matrix, using the eigenvectors put together as a matrix, inverting it, and that's one way to obtain then the diagonal form. We cannot always diagonalize a matrix. For example, if you consider the A matrix 0, 1, 0, 0, so this is not a diagonal matrix. If we try to diagonalize it, the eigenvalue, the only eigenvalue is 0. If you look at the eigenvector A minus 0I times x equals 0, but then this is really AX equals 0. If you write this down, 0, 1, 0, 0, 0, 0, the solution to that is that x1 is arbitrary and x2 equals 0, because this is 0 x1 plus 1 x2 equals 0 equation. So it means x1 is arbitrary and x2 is 0, which means that the null space of A minus 0I equals to the span of the vector 1, 0. It's a one-dimensional subspace. And that means that we cannot create a basis for the whole R2 space, because that's two-dimensional and we would need two basis elements. And for the same reason, we cannot create a P square matrix that we could invert in order to calculate the diagonal matrix. So this is an example of matrix that cannot be diagonalized. But what we see is that at least this is upper triangular. So now we see what's the problem with this. Well, clearly we see that it's a repeated eigenvalue, what we had here. This actually comes from lambda square equals 0 as a solution. So you might suspect that the problem is that we had a repeated case, and yes, that's actually true. What we have is that if, or at least it's half true, so if the dimension of a vector space V is n, and we have a linear operator T on it, and it has exactly n distinct eigenvalues, so all the eigenvalues are different and they don't repeat, then T has a diagonal matrix with respect to some basis. So the proof of this is kind of trivial based on the previous explanations. What we have is that the eigenvectors V1, Vn are linearly independent, or this list is linearly independent. They are all different and non-zero, and that means they form a basis, since there are the same number as the dimension of the vector space. And what we have is that in that basis, T is diagonal. Let me state the following theorem. Let lambda 1, lambda m denote the distinct eigenvalues of T, linear operator on V. Then we have the following equivalent statements. So we have the first one, that T has a diagonal matrix with respect to some basis of V. The second one, equivalent to this first one, is that V has a basis consisting of eigenvectors of T. Yeah, we already know that if T is diagonal in that basis, then the basis elements are the eigenvectors. So these are equivalent. The third one, equivalent with the previous one, is there exists one-dimensional T-invariant subspaces U1, Un of V, such that V is the direct sum of these subspaces U1, Un. This is actually from the previous section. We looked at these invariant subspaces that we obtained. Also, actually from the previous section, but also in this section, we had that these subspaces were actually the null spaces of T minus lambda operators. So we have V as the direct sum of null spaces T minus lambda 1 I and the direct sum with the null space of t minus lambda mi. And then the fifth one is that the dimension of V equals to the dimension of the null space of t minus lambda 1i plus adding together all the dimension of these null spaces. So this fourth and fifth is also trivial, that the dimension, direct sum and the dimension comes from some consideration a long time ago. What's maybe interesting here is that we are talking about some one-dimensional subspaces, and then later we talk about some others that are not necessarily one-dimensional because we are adding together their dimensions. So what we have here is that this set is kind of trivial, how the direct sums work, and also this set of three statements we looked at before. What is maybe new here is how to go between these two sets. So in the proof we just show the equivalence of 2 and 4. So what we have from 2, if 2 is true, then we have B basis of V. Let's say that we have n vectors, since it's n-dimensional, usual notation. These are the eigenvectors of T. So then what we do is we group together eigenvectors corresponding to the same eigenvalues. So let's say that we have lambda 1, and then we have eigenvalues, let's say v1, vd1. Then for lambda 2, we have vd1 plus 1, vd1 plus d2. And then what we have is that we have a subspace u1 as the null space of t minus lambda 1 I, and its dimension is then d1. Similarly, from this we create u2 subspace as the null space of t minus lambda 2i with dimension d2, and so on. So finally we have lambda m eigenvalue with corresponding eigenvectors vd m minus 1 plus 1, and then the last one is supposed to be vn. And then from here we create, from these vectors, we create um subspace as the null space of t minus lambda mi, which is, by the way, has dimension dm. Then if we choose these subspaces, if we add together them, it should be clear that this is all vector space V, since these V's form the basis of V. And these U's are also independent. What we have is that vectors in different U's independent or linearly independent. This was a corollary because they correspond to different eigenvalues. So that means that this is really a direct sum, and it equals to the null spaces t minus lambda 1i direct sum with all the other null spaces up to t minus lambda mi. There are a few more statements left from this section. For this we need the definition of minimal polynomial from a previous chapter that we didn't cover. So what we have is that p of x is a minimal polynomial of t, a linear operator on V, if it is the smallest degree monic such that p of t equals actually the zero operator. This is a theoretical concept, the minimal polynomial. It is somewhat similar to the characteristic polynomials, but not always the same. So let me show in an example that this is not the same as characteristic polynomial. For example, if you have a 3 by 3 matrix A, which is actually a diagonal matrix with 2 in the diagonal, then the characteristic polynomial of this matrix, so that's the determinant of xi minus a, it equals to x minus 2 cubed. And of course we only have one eigenvalue, the lambda equals 2. But a minimal polynomial, so this is the characteristic polynomial, But to look at the minimal polynomial, well, right now we don't have a procedure for finding a minimal polynomial, but you can try, for example, that x minus 2 is a minimal polynomial, since if you plug in a into it, that's a minus 2i, you get exactly the zero matrix. So this shows that you can get, for example, the minimal polynomial by just considering a factor of the characteristic polynomial. Unfortunately, this is not always true. So let's see another example. This kind of shows that minimal polynomials are not something trivial to calculate with. You have to be careful. So now let's consider a 2 by 2 matrix 1, 1, 0, 1. Again, first the characteristic polynomial, which is the determinant of xi minus a. So this is the determinant of x minus 1, 0, x minus 1. It is a diagonal matrix, so the determinant will be x minus 1 square. And you see that 1 is a repeated eigenvalue. But you can also see that p of x equals to x minus 1 is not a minimal polynomial, since if you substitute a into this, you get a minus I, which is 0, 1, 0, 0, and that's not the zero matrix. So minimal polynomial is somehow related to characteristic polynomial, but it's not equal to that. You cannot just cancel some factors and get the minimal polynomial. So first we have a lemma saying that let T be a linear operator on V, where V, the dimension of V is n. V is a vector space over an algebraically closed field F. So then what we have is that if lambda scalar is an eigenvalue of T, then lambda is a root of the minimal polynomial Px of T. So the proof is very short for this. Let's have a V vector, which is a non-zero eigenvector of T, associated to eigenvalue lambda. So what we have is that TV is lambda V. We also have that, for example, T square V is lambda square V. And then in general, what we have is that for any polynomial P, we have that P of T of V equals to P of lambda V, because of the linearity of T and this property that if we apply T several times, if you multiply it with a scalar, so basically if you have a polynomial in T, after you apply it, you get a polynomial in lambda. Then for the minimal polynomial, what we have is that P of T equals to 0, but then P of lambda times V equals P of T V equals the 0 vector. And since V is not 0, then the only way possible is that P of lambda is 0, which proves the lemma. Then the big theorem, last big theorem in this section, is a statement saying that if you have a linear operator T over the vector space V, so V is an n-dimensional vector space over the algebraically closed field F, then T is diagonalizable if and only if the minimal polynomial for T has no repeated root. So looking back at the previous two examples, for this diagonal matrix, we got minimal polynomial x minus 2 with no repeated root. And yes, the A is diagonalizable. Actually, A is already diagonal. For the second example, I didn't mention what a minimal polynomial is, but since x minus 1 was not minimal polynomial, then that means the smallest degree could be the quadratic. And clearly, what we have is that P of x equals x minus 1 square is minimal, since it's already characteristic. So it's minimal polynomial because that's the smallest degree where it's nullified the A matrix, and it does have a repeated root, and that tells us that A cannot be diagonalized, no matter what other basis you can try to come up than the standard basis. So this is a very nice theorem that we have here. The proof is actually quite long and very tedious. One direction is easy, the other is not. So for that reason, I'm not gonna cover it. There are a lot of small details that I don't think is of much use for us to calculate with. There is, although, a corollary to this theorem that I want to mention, and that's that if T is diagonalizable and U is a T-invariant subspace of V, then T restricted to U is also diagonalizable. So the proof of this theorem is much shorter, and it explains or how we can use the theorem. So we consider Px minimal polynomial of T, then that means that P of T equals to 0 operator. So then if you have any vector U in this T-invariant subspace, then of course what we have is that P of T applied to this U vector is also 0, since the whole P of T is 0. But then when we restrict this to the U subspace, that's a 0 operator on U. So that means that when we consider P minimal polynomial, let me denote it with P star, minimal polynomial of T restricted to U, what we have is that since P of T is also 0, that means it must be a multiple of P star. So P is a multiple of P star. P star is supposed to be the minimal. P might be more than that. P is a multiple of P star, and then P has no repeated roots according to the theorem. Then that means a smaller polynomial, by throwing away some factors, can have no repeated roots either. But then if P star does have no repeated roots, then that means that the restriction of T to U is diagonalizable. This is the end of section 7.2. After this, we are almost finished with this chapter. We will continue with a few more remarks, especially about real vector spaces that we usually work with, and what happens when we have complex roots, and some small remarks about commuting linear operators.